Our mechanism is a symmetrical 3-bar crank slider system that is able to open wide enough to accept a fruit with a 3.5-inch diameter and fold over into a closed position which cuts the stem off of fruits. The purpose of this mechanism is to be able to make harvesting fruits from trees easier. It provides safer harvesting from hard-to-reach places of a tree and ease of physical labor for farmers. Our kinematic specifications are: the distance between point P and Q of the output rockers must be 5 inches. The distance between A and B must be able to be actuated by an appropriately sized actuator of less than 1 inch. Ground node O2 must allow for only rotation, and point .04 must allow for only linear translation. Our synthesis was done using a graphical approach.
For our kinematic analysis, we chose to analyze both the displacement of node O4 and the angle between the two output links L4 and L5 with respect to time. This is so that we know the state of the output angle at a certain time, and we are also able to determine the length of the motor arms for driving the mechanism. From our results, we are able to see that the range of motions for the output links are between 0 to 134 degrees, and the range of motion of node O4 is 0.27 inches.
For the force analysis, the goal is to find the required input force to cut through the fruit stem. Looking at a chart for the maximum shear stress of various woods from woodworkweb.com, we find a value of 2000 psi for the maximum shear stress, as that is the average for US hardwoods. Assuming a typical fruit stem to be 1/8 of an inch diameter, we can calculate the required shear force to be approximately 24.5 pounds, or about 100 newtons. Analyzing this system as a 3-part crank slider mechanism, we can use a system of equations to solve for the required input force, as well as the forces at each joint. We used Excel to solve for this system of equations to find the required torque on the input links. Through these calculations, we find the force required at pins A and B to be 85 newtons at both locations.
We decided that the best possible pin we could use would be a 3/16 diameter zinc-plated steel fastener from McMaster. This pin would would be able to withstand a strength of even up to 7,664 newtons, which is much higher than our calculated forces for each one of the joints, which was 56 newtons. This would give us a factor of safety of 136. That factor of safety is a lot higher than needed, but due to the fact that our mechanism operates with comparably small forces, this is understandable.